Okay, welcome everyone to our last lecture for this semester. Congrats to you that you managed to go through a pretty, I'm sure, intense and difficult semester because of this course and the other courses you have. This is the last lecture. I think it's going to be fun. We may add only one required reading for you, okay, from this week to the quiz, which is very little, I think. Yeah. And today's lecture is focused on language. What is the role of language for robotic learning? Okay. Clearly, language is very useful to describe goals. So many times in this course, we assume that the goal is an image, but this has dramatic limitations. For example, imagine I tell you, put my watch in the drawer, and then I show you a picture of a closed drawer. I mean, clearly, it doesn't convey the fact there is a watch inside. Okay, so this is a limitation. The most natural way humans communicate goals to one another is using natural language. And indeed, that's what we do. We program each other every day, our co-workers and our colleagues and our children and our parents and so on, by natural language. Not only we give them the final goal, for example, put my watch in the drawer, but we also give them intermediate goals. Oh, I cannot find the watch. Oh, the watch is right now in the kitchen counter. Go and fetch it. Oh, I cannot open it. Oh, focus on the red button it has on the top, and so on. Okay? And the reason a language is so effective for humans is because when I tell you focus on the red button, you know exactly what a red button is. So you can ground noun phrases to visual scenes, right? So this language is not just a bunch of symbols, but they're grounded on actual visual experiences. And this visual experience is not just identification of objects, the dirty mug, the empty bottle, the stove switched on and so on, but it's also knowledge on how things work, okay? So if I tell you, oh, focus on the red button on the top, you're not going to start blowing on the button, for example, okay? You can blow on, boiling hot egg, for example, but you wouldn't be blowing a button because you know the affordance probably going to try to touch it and pick and so on, okay? All right, great. But by the way, anytime you have questions, you just raise your hand. So far, things will make sense, I think, okay? So we'll visit 3 different sets of approaches in this lecture. The first is the simplest one. We'll directly ground language, map language to actions, okay? And we'll learn policies that are goal conditioned, and the goal will be the language itself, okay? And the second is we'll map language to simpler language and then to actions. For example, imagine I tell you, make the table for dinner, and you're like, okay, how I'm going to make the table? Then I'm going to start telling you, okay, grab a white plate, put in the middle, take a fork, put to the side, and the knife to the other side, and then fold the napkin on top, and so on. So I can give you sub-goals in natural language. Is that correct? And the third approach will be map language to some goal abstraction in some way, visually grounded abstraction, and then from there to actions. This is the third. So you would, when I tell you, so 2 things, so two points I want to make. Imagine that you have a helper in your house, or you're a chef in a restaurant, and you want to teach them how to make the table. I mean, the truth is that if I tell to a human being, okay, put a plate and then put a fork and so on to the left and to the right, they're probably going to do the right thing. Now, if you put to the robot, it's going to dump the fork, and the fork's going to be diagonal here, maybe touching a bit the plate. Also, the spoon, God knows, is going to be this way or that way. The napkin is going to be folded, God knows how, etc. And also, there is no reason why the fork and the spoon will be equidistant from the plate. You just the robot can do whatever it wants, and it's still one is going to be on the left and the other is going to be on the right. It is extremely exhausting to describe the scene in language. There is this quote that an image is like 1,000 words. If I show you a picture, or I show you a demonstration, or a picture of a table done and ready for dinner, all those details will be there. okay, exactly about the parallel and the distance and the key points of different utensils and so on. And I mean, usually when you have a helper, I don't know if you've seen, but I've seen when a new person goes in a restaurant, first you show them the first day, you see, here's how you're going to make the table, and you don't talk, you don't say the fork goes to the right, you just show, okay? And they see, and then next day, you don't do language sub-goals, so make fork to the right and so on, you tell them, you just do what we did yesterday, okay? And so basically now the language, make the table the way we did it yesterday, is grounded to the memory of that person from yesterday, which is supposed to be retrieved and matched to the current situation so that they are able to repeat the task, okay? So we don't have a lot of models that I can describe to you with such associative memory, despite the fact that it's clearly extremely important for, let's say, robotic learning. The reason we don't have good memories and memory models is because computer vision doesn't work yet that well. So you may save the image, but you don't have a clue where's the fork, where's the key points. You cannot do this matching, so you cannot use that memory yet, because our feature representations, visual feature representations, are not as fine-grained. All right, we can find the plate and we can find some fork, hopefully, but we don't know about the key points of the fork and the pose. We have very good vision models for the human body and the hand, but not very good vision models for any object out there in the world. Okay, so even if I was saving those memories, I wouldn't be able to utilize them. Okay, so we explained this point. And the second is the following. When I talk to you, is the point we actually made also yesterday. When I give you language, before mapping language to actions, you make sure language makes sense to you. Okay, so you have an idea of what I'm looking for. So this goal description, kicks in. And if it doesn't make sense to you, you ask and raise a error, let's say, and otherwise you go ahead and execute. So let's visit those three different streams to see what they can do and what they cannot do. So here is a wonderful paper from 2021 in Coral, Conference of Robot Learning. Coral is a very interesting conference that was founded a few years ago. There are tons of robots conferences like ICRA and IROS and so on, but they are not focused on learning. So Coral is focused precisely on machine learning and robots, and how do we pursue learning-based methods for robots to execute tasks. Is that clear? Okay. So what does this video show? This video shows the result of this paper, but also the goal. So we pursue a robot agent that, given diverse descriptions of diverse tasks, and that you see here in quotes. So this is the instruction that the policy is conditioned on. The robot executes the instruction. Is that clear? Is that clear, guys? Do you see the input and output? So the input is a visual scene and the language instruction, and the output is the actions of the robot to rearrange the scene so that the final resulting scene satisfies the instruction. Okay? All right. And Clipboard is a marriage between the Clip model, this very large-scale OpenAI model that just encodes text into 1D embeddings, as we said yesterday, in the visual image into, again, 1D embeddings, and trained with contrastive learning with 300 million of captioned images. Okay, do you remember we talked about this? And transporter networks, which we also know and we love, and so on. So this is a marriage between Clip model and transporter networks in a way that I'm going to show. And not only works in simulation, but also works in the real world. This policy has been trained supervised, much like transporter networks that were trained supervised from kinesthetic demonstrations. Each demonstration has a task, a description, okay, a language instruction, and is paired with pick and place locations, all right? And the policy network, the language condition policy network will describe, is trained to predict the corresponding pick and place locations. And one task can be comprised of a sequence of actions. All right, so you may need multiple pick and place, as you see here, to clean the, what is this now? These tiny little brown beans. To put them in the circle, you need multiple consecutive actions. All right, and by the way, why I call this pick and place? Sees clearly in the case of beans, we're just swapping Does anybody want to say something about that? Yeah?
You can consider the sweep just as like start the groove in one place in the pick spot and then move it to the play spot.
Yes, precisely. So your calling is saying it doesn't need to be a pick and place for you to use transporter networks. Any behavior of a robot that can be described with two gripper poses, beginning pose and end pose, all right, with some predefined motion between them. For example, between pick and place, also there's a predefined motion. You're supposed to lift above the ground a certain height and then go, and the rotation, of course, is predicted, as we said, then the place location is predicted. So he said, in any of those, you can use this type of networks, transporter networks, and indeed, that's why they're so versatile, right? Because everything can be represented as pushing or as pick and place, so as the, and so on and so forth. Even opening bags, as we saw, rearrangement of ropes, etc. And again, here we don't have a sim to real jump. No, we train with real world demonstrations, and you don't need that many. If you remember, transporter networks were also not trained from that many demonstrations. And that's it. So it's not that we train in simulation, then we test in the real world. I'm just showing that this supervised imitation learning works both in simulation from simulated demos, teleoperated data, and in the real world. Okay. All right. So now we'll go and see the architecture of that model. So yesterday, your colleague said that in this case, I think he was referring to this model, the language would be condensed into 1D vector. And then I was saying no, and I had it wrong in my mind. Indeed, the whole instruction will be mapped using the language encoder of clip into 1D vector. And as you see, this language and visual encoders of clips are frozen. You take them from clip and you don't fine tune them anymore. Okay, and just to remind you, clip has two encoders, one language and one visual. Do you agree? And the language one is looks like a transformer, and the visual one, I think they use the ResNet. But you can also repeat the training with any backbone that you like. Okay, now what happens? So they say that this model has two pathways, the what pathway and the where pathway. Much in the human brain, we have the ventral, which is about what and recognition of objects, and dorsal, which is about execution and procedural knowledge and so on. So the top path, that is clip, is the what, and the bottom path, which takes as input an RGBD input, is the where. Okay, and the top you feed just the RGB image, and in the bottom you also feed the depth channel. All right. Okay, so what happens exactly here in the architecture? At the top of the visual encoder, you have 7x7 by 2048, all right? And you take those language encoding, which is 1024, and what you do is you tile them. So you replicate the same vector in the 7x7 grid, and then what you do is point-wise multiplication. So why you do point-wise multiplication is as if you're searching for those language features anywhere in the image, much like clip is doing point-wise multiplication between, they collapse the 7x7 into an extra, visual vector, so we don't use that. And so you do this tiling and so on, and point-wise multiplication, you do this for 3 layers. And then those features here are also concatenated with the features extracted from the RGBD. And you use the model to do precisely the same thing that you did with transporters to predict peak locations. And once you predict peak locations, you crop them and you feed in the model of that crop, and you do you rotate the crop 36 times, and you do cross convolutions, and you train to predict placing locations, much like the transporter networks. Okay. Is that clear, guys? So this guy basically here is spitting out both the peak heat map as well as the place heat map. Okay, once you crop here and you do cross correlations. So let me visualize those peak and place heat maps for you. They actually have a wonderful website where you can see those visuals. So here is pack all the yellow and blue boxes into the brown box. So the peak heat map lights up on the blue box in this time step. And the place heat map, once you crop around that guy, and you do cross convolution, it's going to light up at those locations of the brown box. And once you put all the blue boxes, hopefully next the yellow box is going to light up. Does this make sense? Because this is a multi-step execution. It's a multi-step policy that has a lot of pick and place. All right? Okay. And at every step, you use the same backbone to predict the next pick location and the next placing location. So again, here for the white tape, the pick location lights up on the white, and the place location lights up on the box, and so on. And here is the cloth, and it says pick it in this way and place it somewhere there. You see here the placing is not on an object, is on a, white space. Of course, the demonstrations would be placing the cloth in different locations of the white space, but because you train with softmax, you can handle multimodality. It's okay for the placing heat map to have multiple activations, let's say, on different pixels, and so on and so forth. And here is for the swiping. They say, swap the bins into the yellow zone. So you say, place here your gripper, and then push and release it here in this placing location. And indeed, the bins in this way are going to push toward the yellow, the yellow zone. And if it was the opposite, then you should have placed here and pushed towards the other direction. Correct? Okay. So here are some more examples. And as you saw, it works well. Now, we have downloaded this model, and the truth is that because it is trained with very, very little data, I mean, if you change the background, for example, of the table, the background color, I mean, immediately the behavior is much affected, okay? So there is a lot of, and I'm going to show you some more results later, but still, I think this is very impressive because they found a way to utilize a pre-trained model from passive data, just internet images, into the what pathway for robotic manipulation. Because when I ask you to do a task, the first thing you need to do is to understand, the things that I'm talking about. And Clip knows a lot about the world. Knows about cell phones, knows about codes, and et cetera, et cetera. So why shouldn't you not use this type of knowledge? This is the idea here. Very good idea. Okay. All right. So there are some limitations that we said. For example, a particular place where the clipboard model is not good is it doesn't understand well when it should be done and it should not be continuing executing because it doesn't have a good idea of the goal matching. Like, yes, now I really satisfied the goal. So very often when they evaluate it, they use an oracle stop sign. So there is someone that was watching and say, yes, now you execute most of the task. I'm going to stop because then if you continue, God knows what's going to happen. Okay. Okay, so now we go to the next topic, which is about the following. What if the language that I give is very complex? And indeed, you saw some of this language was complicated and you require multiple tasks. And if I tell you, for example, pick all the Coca-Cola boxes and put them in the fridge, then you need to pick, move to the fridge, open the fridge, put the one, then go back, pick the one, and put it back and so on, okay? And so it does make sense that a big complicated language command can be broken into sub-goals, okay, much like a program, and issue those easier sub-goals to the robot, okay? Do you agree with this? I think it is pretty obvious with a for loop. So we're going to do a small digression and discuss language models, and then we'll show how to use those language models for issuing those language sub-goals so that we can break a complicated task into simpler subtasks, okay? Does anybody have an objection here? Okay. So what are language models? Language models are very simple models that take as input a sequence of words and feed them into a transporter, and they're asked to predict the next word. And I mean, this is not new. This has a very long time people have been training those models. There are two variations. Usually when you talk about language modeling task is predicting the next token. If they talk about masked modeling, means that you have the surrounding context, let's say X1 and X2, and you mask the middle tokens and you ask the model to predict them. All right. So these are two different things. One goes from left to right and the other predicts the masked tokens. And here is another variation of the architecture. So this is called decoder only model. Okay. You just have the token and you do self-attentions in all of them jointly and so on. And then there is another variation called the encoder-decoder, where the input, known input, is contextualized on its own using an encoder. And when you want to predict, then you cross-attend to the input features through cross-attention operations. I don't think there is a tremendous difference between those architectures, but I just want to tell so that you are not surprised. For example, the T5 model, which is also very famous, uses this type of architecture, okay? Now why language models are so, let's say, famous recently? Well, because there has been a huge explosion on their size. And by size, we mean number of parameters, okay? Yes. So, and as the number of parameters goes up, the number of training data also goes up, okay? So they can benefit from larger and larger training sets. We're talking about, strip the whole internet and fit to the model. No matter if this is web pages or it's code or it's any type of text you find, okay? Wikipedia, books, news articles, and so on and so forth. So natural or non-natural language like code, okay? And you see how the size of the model scales. And this is the GPT-3 family, all right, in the blue. And you know what? It turns out this is log scale. This is a huge boost. Let me see if I have another picture. No. And you see the results here. Now these models can generate whole articles, and it's very difficult for the human to tell whether the article is fake or not. So what I show here as gray is the conditioning prefix that you give to your trained language model. And what you see there as the black, is the generated text from the model. And on average, with only 52% success, we're able humans to tell whether the articles were real or generated by GPT-3, okay? So this is very easy now to generate fake stories. Okay, and here on the left, we show an article that really humans could not tell that it was from GPT-3, and this one that actually were able to say 61% of them thought that it was generated by GPT-3. So the left really fooled humans quite well, okay? Is that clear? This is just generation of words. All right, perfect. So the scale is nuts. Yes, and of course, the amount of power you need to train those models is, again, pretty crazy. And so there are interfaces that you can use to actually test this model by querying it, and you go to the OpenAI servers and you get back the answer, okay? Because you cannot actually host this model yourself, which is very interesting. Now, what are the implications of those very, very, very large language models for us, all right? So, okay, we trained this model with all data we could find on the web, how we can use it on downstream tasks, correct? So the standard paradigm of previous models, or at least what we've been doing it since till 2 years ago, is that we take a model that has been pre-trained and we fine-tune its weights on the few data of our task, correct? Do you agree with this? Okay, so, and we do gradient descent, and we may decide that, so we may decide to fine-tune all the weights, or we may decide to fine-tune only the top layers. That's fine, but that's what people used to do. Now, it turns out, with those extremely large language models, something very, very interesting emerges. Which is what? At test time, without updating at all the weights of the model, you can repurpose them, its knowledge, for different downstream tasks, simply by adapting the prefix that you fit to the model, okay? Imagine now you train your GPT-3 large, and now you want it to translate. What you're going to write to the model is translate English to French, cheese, what is in French, and you wait for the model to spit out fromage, let's say, okay? So that's one thing you can do, and this is called zero shot. And there is absolutely no fine-tuning at all, okay? You just take the pre-trained LM and give it the following prefix. And what people have found to work better than that is to actually, instead of just describing the task in natural language, like translate English to French, you also give it some examples of the task. For example, you give it examples of the sea otter is l'eau de mer, and now tell me about the cheese, okay? And why this is interesting? Because look at the prompt. The prompt is just a sequence of words, by the way, where at every time the example, it's comprised of multiple examples. So here is a prompt with more examples here. And at the end of each example, you put a special sign, a special language token. And what is very interesting is that actually this works. And why this is interesting? Because the test data, which is these prompts, are very different from the training data. Do you see? It is very unlikely that the GPT-3 was seeing this type of exactly text at training time, because the different examples have very low probability between them. Like, who would first say, okay, here is the C, here is how we say cheese, here is how we say mother, and so on. Do you see? There is very low probability transitions from one example to the other. Okay, even if you would consume whole dictionaries of English to French, what GPT-3 probably has consumed, the words would come in alphabetical order, not in arbitrary like here. Now, so the interesting thing is that this in-context prediction emerges and it actually works. Now, what is the limitation? I mean, this prefix is fed to the model, so it's better feed in your GPU. So you cannot dump there 1 million examples. Say 100 examples, because all of those need to be jointly contextualized to predict the next token with transformer layers. Is that clear? All right. Okay. Yeah, so this is now the performance as you vary the number of examples in that context window, in that prefix that we just discussed, and performance improves with the number of examples. Okay, zero shot means I just describe you the translation task without giving you an example of, English to French word paired, and then the others have also this type of examples. So now, how does this new paradigm, prompting, so we'll call this prompting, compare to pre-train plus fine-tune? Now, first of all, we need to acknowledge a huge problem here, which is it is really hard to evaluate those prompting models, because if you prompt it and I prompt it, we may design different prompts and the model may behave differently. Okay, so now it's very hard to say that the model failed, because you can always say, oh, your prompt is not good enough. Do you see? So if you give it a different prompt, and there's a whole new research field called prompt engineering, where they really search on what prefix to feed to the model so that they have the best possible performance actually on the task. Is that clear? Okay. So this prompting is also what we're going to use for robots, and I'm going to show you what type of prompts we're going to be feeding in just a second. So before we jump to the robots, let's just see what happens in prompting in natural language. So here is one task that we care to solve, which is trivial question answering, general question answers about, pop culture and other knowledge, history, music, and so on. So you want your GPT-3 to also know about these things. And here is the interesting thing, that the fine-tuning, the state of the art, does worse than the few shot. By few shot, they say 64 examples on the prompt, non-fine-tuned, 175 billion parameter language model. Okay, and the insane thing is that performance dramatically depends on the size of the model. Okay, as you see, the more billions of tokens you add, the higher it is. Do you see this graph here, how it goes? And okay, here you stop, because you already beat the supervised state of the art. Okay, do you understand those implications, guys? All right, so that's one task, trivia question answering, but there are other tasks. For example, what about translation? Well, in translation, the state-of-the-art supervised model is still much better than GPT-3 on English to French translation, as you see, with 45.6 bolded, okay? And the thing is that the improvement haven't plateaued, and the expectation is as you scale these models, you keep improving okay? That's what you see here. Okay, and now let me show you another. Do you have any questions? And here we'll show you different languages that you care to translate from and to. What about comprehension question answering? So this is a very interesting task. And here you see that the state of the art does much better than GPT-3. And indeed, GPT-3 is not very good on actual question answering here, comprehension. Let's see. Yes, how do you understand a piece of text, etc. Now, I want to tell you something. There is a recent trend, actually not that recent, it's been around for like 2-3 years, on language models to augment a parametric language model with a huge external memory of question-answer pairs, which makes tremendous amount of sense. Which means if you ask me, when was Michael Jackson born? Okay, so I will go and query my external database of question-answer pairs, retrieve the answers, and answer the question. In this way, I save knowledge not only on my weights implicitly, but also explicitly in a format that is easy to retrieve on demand, of course. Yes, these models have been doing super well. We're talking about memories of in the form of 300 million question-answer pairs. The most recent models, they go through a text. Let's say you give me a passage, okay, and I read it, and instead of saving phrases of the passage in their memory, they convert the passage into question-answer pairs. For example, we're in Mississippi, 1937, and then you convert this with also trained models. So you generate questions. For example, when is the passage about? Oh, 1937. Where is it taking place? On Tennessee or whatever. Do you see? So you save the passage in terms of question answer simply because this is the more easier to index form for the language model later to use for comprehension question answering. Okay. So just to tell you that, you know, the language model community does use this insanely large external databases or memories, okay, of information to be able to do question answering. And the beauty is that these guys can scale without you need to add your computation increasing. Because as you scale the language model, you pay more money on training it and so on, while if you scale the external memory, you don't. And in fact, they have shown that you can shrink the model, you can make it much smaller with the same performance if you have those external memories. Is that clear? Okay. Now, here is now the important question we want to answer. Are language models, yes?
Is it querying that like external database with like an attention mechanism, or how is it doing that querying?
Yeah, so the memories are typically pairs, question answers. So the question is the key and the answer is the value. And your input sentence is the query. And the query is doing some inner products with the keys and then retrieves the answer and spits it out. But it's not this simple, just weighted average. They also can, you know, you do more dense cross attentions to adapt it. Maybe also I ask you more complicated question, which requires for you to index in 2 different parts of the memory and so on. So you go back multiple times. But yes, pretty much is like that, through attention. Yes. Okay. All right. Other questions? Okay. So are language models useful for robot learning? There has been a lot of recent approaches that use language models for robot control in the following way. They assume that the low-level skills are given. For example, the robot can move around and climb the stairs, can pick up an object, rotate, and so on. And they build on top of those skills high-level planning algorithms. Okay. And let me give you an example. You take your GPT-3, all right? And then you prompt it. And now the interesting thing is, how do you prompt the model in our case? Like for translation, we saw how you prompt. So here you prompt in the following. You say, the task is to shave. And step 1 is grab the razor. Face. Then the task is brush teeth. Okay. You need to write this prompt. Now, as you need to write this prompt and you fit as a prefix, then you ask the language model. Okay, so the brush teeth is the test task. So you're not going to put, of course, this on the prompt. But then you query the language model, and then it's going to be able to spit out analogous plans for your test tasks. Is that clear? Okay. Yes. Great. So, and people have shown that, yes, look, if I have this type of tasks and the skills are indeed there, that I'm able to move an agent around and actually execute all those tasks that my language model spits out. All right. And the interesting thing is that you take GPT-3 pre-trained. You don't change at all the weights. You just prompt it with task plans. Is this clear? Okay. Now, let me give you a more recent paper that does similar thing, which is called Inner Monologue. And let me tell you the difference between Inner Monologue and the previous approach. Instead of just feeding as input to the language model, the task plan and the prompt, and then the language model just spits out sub-goals and the robot executes them, and this is all open loop. Now the robot can feed back input to the language model and can say, oh, I cannot find the razor. Oh, I failed to pick up the razor, and so on. Okay, so now the human puts a task, which is, can you bring me a soda? And the robot says, okay, I need to find the Coke. I need to pick up the Coke. Oh, the action is not successful, and so on. And then you say, oh, I see an orange soda. And then there is no Coke, but there's an orange soda. But is there no Coke, or is just he failed to pick it up, the Coke? I'm not sure what's going on here. Let's see. Oh, conveniently, this is not a Coke. Because if it was not a Coke, we would have a problem because we actually cannot pick it up in any case. So here's like, okay, there is this soda and so on. And then you're like, okay, go and pick it up, etc. Now here is the interesting thing. When this model is deployed, they often use ground truth perception. So ground truth success detectors. I told you that Clip also had difficulty with evaluating success or not of a task. Does this make sense? So basically, let me give you another video.
We present inner monologue, embodied reasoning through planning with language models. Imagine the thought process when a person tries to solve some task. I have to unlock the door. Let me try to pick up the key and put it in the lock. No.
Okay, so here, what they say is that in the same way that when you execute a task, when you get stuck, you're like, oh, I think the key doesn't open the door, okay? And you give feedback to yourself to prompt it to execute, to predict alternative action, okay? Which makes a lot of sense. So they say, we're going to do exactly the same thing with the language model. Instead of just taking the task, asking the language model for a task plan, and asking the robot to execute it, we're going to go and be giving feedback back to our language model. And because this is a language model, the feedback also needs to be in language format. Does this make sense? Everything will be in language. Okay, so here, for example, I mean, okay, now they talk about the previous work, but basically the feedback would be something like, I cannot find soda, and the description of the scene will be a list of objects. I see these objects and so on. And the interesting thing is that you need to decide the prompt for this. So whatever the prompt you decide is, and now the interesting thing is that this video has some prompts like that. So let's see. So let's see again the skills. So they assume that these skills exist. So basically you can call those type of skills, okay? This is the skill library that
For example, we can provide descriptions of what objects are present in the scene. The language model planner may also ask clarifying questions if the instruction is ambiguous, such that it can replan based on the question and the answer. Additionally, the success detector can also provide indication whether the last action was successful. If not, the robot may need to execute that action again and proceed to the next steps. While any feedback that can be expressed in textual form can be incorporated, we focus on 3 types of environmental feedback in this work. The first one is passive scene description, which broadly describes environmental feedbacks that are consistently provided and follow some structure, such as object recognition. The second one is active scene description, which describes the unstructured feedbacks provided in response to the questions asked by the language model planner. The questions may be answered by a human or by a visual question answering model. In this work, we focus our analysis with answers provided by humans. The third kind of feedback is success detection. This can either be a trained model or an engineered solution using heuristics. Importantly, the entire process only requires few-shot prompting and no additional training for the language model. Here are some example runs of the proposed method. In the simulated domain, here the task is to put all the blocks in the balls with matching colors. Notice that the policy fails to place the pink block during the first time, but quickly retries and succeeds in the second time.
So here's now the interesting thing that you need to, for each task description, you need to write a different prompt. For example, in this type of setup, you need to give prompts of the form, oh yeah, my goal state is, and the goal state needs to be described in terms of special concepts between objects, okay? And then usually the scene description has to do with just a list of objects. So you run a detector and you say, I see this object and this object and this object and this object. And this is also prompted because somebody can totally describe the scene in terms of who is in left of whom, etc., or who is on top of whom, right? So the prompt, though, usually they just put a list of objects, let's say. And yes, and then in the scene, in the success, then you just go back to the original goal state and you say, okay, I just succeeded on the first goal, sub-goal, and then the next sub-goal, and so on. Okay, so the problem is that this prompt engineering is all humans, and we're talking about prompts that are like many pages long, like 3 very dense written prompts, and also there's no train and test. So the way this works is that you come up with a scene description. Let's say I want to put cubes in balls. Then you start engineering prompts. Then you ask the language model. Then you see what you get. And you reiterate on the prompt. And then you're like, oh, yeah, look, I was able to solve this. So there is no train and test, essentially. For every task description, you go and you engineer a prompt, etc. Does this make sense? So you cannot compare against those language models because everybody could say, oh, yeah, for this scene description, I would give a different prompt. Do you see what I mean? Okay. But I think you should watch all this, yeah, so for example, here the scene description is different. There's no left and right because left and right was relevant in the previous scene, but not in this scene. So here the description as given also by the prompt and as repeated is just a list of objects, okay, without their special arrangements. Does this make sense? So you need to move every object, and then instead of saying, oh, the done object is mastered, while before you were saying, oh, the completed sub-goal is A to the left of B. Okay. So you need to engineer a prompt for every task. Yeah, and the same.
Forces another failure when the robot tries to pick up the code, and the robot is able to recover from its failure again. On the table. When the robot goes to the table, the human operator says...
Yeah, so now let me show you what is the problem here. Imagine that the human, so this is an example here of the inner monologues. It says move all the blocks. This is the same task as we saw earlier. And, here the goal is described in terms of which object is in which ball. It's not about left, right. It's not about, lists of objects. It's about which object is in which ball. And this prompt, it is again about all putting objects in balls. The difficulty is that imagine that the broad is in gray, and now the human tells you, put the strawberry to the right of the one cube and to the left of the apple, right? If we follow the previous prompting idea, then I can always say, oh yeah, take the strawberry and put it now. The first thing to do is put it to the right. And then you put it to the left. And then you put to the right and you put to the left. And you never put it in between the two objects, which was your intended sub-goal. Does this make sense? So planning in the language space is extremely, first of all, it requires insane task-specific engineering of the prompts. And also it's not general. Like, imagine I want you to put a fork to the right of the plate. It's very hard for me to tell you in sub-goals how to put it etc. Okay, like, or it's going to be exhausting. Oh, straighten it up a little bit, push it 2 degrees to the right. Oh, make sure this is 1 centimeter closer to the top of the table, etc. Let alone that you need to be able to execute all those skills, which is actually very difficult. All right, but in any case, what I'm trying to say is that you can go now and read this paper and understand what's going. It's taking a big GPT-3. This is frozen, or this is GPT-3. Actually, it's called Instruct GPT that has been fine-tuned on instructions. Okay, instruction following. And then you prompt it. And the very interesting thing that I would suggest to you is go to the appendix and read those prompts, the appendix of the paper, and then see what happens and what skills they use. And what they showed in their talk is that 90% of the effort goes on the skill learning, and very, very little goes on the, language, let's say. But the truth is that what makes Indino the paper is the language part, because the skill is all about engineering, and there is nothing interesting researchy to show. Do you see what I mean? Despite the fact that this is a big problem. And we'll go back to this in a second. So this is about imagination on language space, much like an inner monologue we do. And indeed, language is a very big, it allows us to do better abstractions. And they say that when the infants are able to talk and understand left and right, they're much better on planning and moving around the house, etc. So of course, there is a very big part that this language supervision plays on the visual representations, okay? So here again, let's say we're going to follow, let's say, a more modular pipeline. I'm just going to show you something else. Again, there are many limitations, etc., but just to see what we can do with language. So going back to the comment of your colleague, the first thing we need to do when you give me a command, such as find the fruits and put them in the plate, is to be able to localize the objects that the person is talking about, okay? And in fact, this type of language grounding models is also used from the previous inner monologue paper that I just showed you. And in fact, this works quite well. It's not perfect, but there has been tremendous progress on this. So this is one thing that we're going to discuss now for the next 5-10 minutes. So what is this problem? The problem is open vocabulary object detection, or else referential language grounding. So both ways they are to refer to the same task. So the idea is that you have a visual scene. It can be in 2D or in 3D, or it can be a video, and there is a description of some objects in the scene. And your goal is to put boxes around those objects, okay? You just need to localize those noun phrases. Is that clear? The problem is clear? Okay. And the same thing for 2D images. This is the clock on top of the shelf, and you want to localize both the clock and the shelf, okay? Does this make sense to you as a problem? I mean, because it's kind of important. If you tell me take all the blue cubes and put them in the red ball, I mean, the first thing I need to know is what is the blue cube and what is the red ball. And there's no reason to take the clip embedding 1D and do these very coarse inner products, okay, and everything to be implicit. I can explicitly say, oh, I think you're talking about this object. When I can explicitly say that, then I can even ask the human, is this what you're talking about? Is this the object you're talking about? So to be able to engage into a dialogue, it's important some things to be explicitly grounded, okay? So we're not saying anything controversial here. Now, the truth is that the field have built fantastic bottom-up detectors. So these are detectors that are trained across multiple, let's say, object classes, and you can just fire those and spit out bounding boxes for a lot of different objects, okay? Now, the truth is that if the object is small, or if I'm referring to like, oh, look at the stain of your pullover, or look at the tip of your nose, or like the tip of your eyebrow, or your knee, and so on, there's no reason the object detector to put a box around that, because I can refer with language to any visual entity in the scene, okay? And indeed, as you see here, our generic object detector doesn't find the clock, and our generic object detector doesn't find the bottle on the vanity, let's say, correct? Okay, so these detectors don't take language as input. They don't take as input what you're trying to find. They just take as input the visual scene, and they spit out instances of the object categories that they were trained on. Is that clear? Okay, now the question is, now that I also have an additional input, where I know what I'm looking for, I'm looking for the clock on top of the kitchen counter. Can I do something more? That's the question. And there has been papers and the models that yes, there is a very trivial extension that you can do in object detectors, where instead of just feeding the visual scene, you feed it as input also the language all right, what you're looking for in that scene. Is that clear, guys? Okay, so what are you going to do? Well, you'll take the scene and you extract patches and you put some transformer or other encoder and you describe those patches with feature vectors. And then you will take the language and you will also describe the words with feature vectors using some transformer or Roberta, or you can also use the clip language encoder to initialize your weights from if you like. And if you want, you can also use a pre-trained object detector and spit out boxes. And you know that these boxes are not going to be complete. You know that what you're looking for may not be part of those boxes. But why do you fit those boxes? Because the whole point is to take the visual scene and tokenize it in some way. Okay, break it into little entities. One way to break a scene into entities with patches. Another way to break a scene into entities with objects. And you may as well throw those tokens together and attend on them. And now all those things are contextualized together. And what you do is you spit out the objects. So what does this mean? You have what these are queries. So these are free variables. These are feature vectors. Okay. And this is how modern detection transformers work in computer vision. And those vectors attend on those set of tokens. And what they do is they decode bounding boxes for the objects. And there is a contrastive loss between the features of those boxes and the noun phrases in your language prompt that actually match the two. And my question is, how do we find the noun phrases in the language input? Which refer to the objects that you're looking for in the scene? Yes.
Some sort of automatic or language model parser.
Yeah, you take a ready chunker, let's say pre-trained on tons of data, and then you use it. And of course, they are not golden noun phrases, but they're good enough. Yeah, that's exactly what you do. Okay, so now you have noun phrases, and you take this noun phrase and you average their words, embeddings, and you have, let's say, a noun phrase descriptor. And when you decode objects, you don't know which one is the plant and which one is the end table. But what you do is you do inner product between the visual features and the noun phrase features, and you train this contrastive loss to essentially do the matching for you. Very natural, right? Much like Clip was doing matching between the whole scene and the whole caption. Here we do matching between the object and the noun phrase. Is that clear? And just to be clear here, guys, if I tell you the plant on top of the end table or to the left of the end table, because you have this language encoder, the plant knows if it's supposed to be on top or below, okay? Because of this cross attentions on the language utterance. Is this clear? Okay, and the architecture essentially is okay, so here is now the interesting thing. You can train exactly the same model for object detection as well. Instead of feeding a language grounding utterance, you can just put a list of object categories, let's say dog, cat, chair, and so on, and then frame object detection as grounding of this list of categories. And again, you can use the same architecture. So you train one model to do what people call object detection, which means finding instances of a predefined set of object categories, here, couch, person, and chair, as well as find localized noun phrases of a referential utterance. Is that clear? That you can see the two problems as being identical if you feed this type of detection prompt, which is essentially one sentence with one listing all the object categories. And of course, you should be able to swap the object categories and their order doesn't matter whatsoever. Okay. Is this clear, guys? And in fact, you can find these architectures. If you see these models called GLIP and GLIP V2, that they are trained with insane amount of annotations, because now you can use both object detection datasets and you can use language grounding and captioned images and train yourself across all data. And they do very, very well. And they do better even than detection models that have only trained on object detection data and not on referential grounding. Is that clear? Okay. And just to show here, oh yes, here. So if you don't use these detection prompts, then you have a sizable drop in performance of 5%. So indeed, framing the task as joint object detection and referential grounding helps you do better referential grounding because you have more training data for your model, okay? That's it. So now you have a model, or you know at least about this family of models, that if you give them language utterings, they go and detect the objects in the scene. And by the way, do you remember that they said, oh, we use an object detector to find the objects? These are the type of models that are being used there, okay? That they take language and input, and they're cross attentions, and the corresponding objects are grounded. So now we know how this works. Do you have any question here? Okay. So now that we know how to detect objects in images, what we're going to do is to generate goals. You remember last time we talked about goal generation, okay? But somehow I had, let's say, skipped over how do we actually found the objects in the first place, which now we know how to do, okay? And there is ready code of all those models are there. You can grab them and use them, okay? And we have talked about energy models, all right? Do you remember? Then we said we're going to train one energy model per concept, okay? And this energy function, does anybody remember what it was, the input and the output of it? What we said on Monday? Does anybody remember when we talked about those energy functions? Yes.
The input was sort of the arrangement of the items, and then the output, well, the output that you used was a gradient where, you know, how the items needed to move to match the concept better.
I see. Okay, very good. Other people? Okay, so an energy function, guys, what you see there as epsilon theta of x is just, let's say, a parametric function, which can also be a network, that maps the object sizes and locations to a scalar energy. Okay, so the output is just scalar. Now, the way we use it, you train it so that you are able to use the gradient of that parametric function over the input so that you can move the object so that they better satisfy the concept, okay? But the parametric function's input is object arrangements as object locations and sizes, and the output is, let's say, how well these objects satisfy this concept. So let's focus on the concept of square that is shown in that picture. If I would feed as input the absolute XY locations of the different nodes, as well as their size. To be honest, here, all objects have the same size because they're all like this type of little squares, so it doesn't matter. The concepts would be very sensitive of where those objects are. So you would have to learn squares being on the left side of the scene and on the right side of the scene separately. Do you see? Because you feed the absolute XY locations. So you don't do that. What you feed is the relative distances between every node and everything else. Okay. So this also you can find as a relative attention on transformer architectures. Transformer architectures have a list of visual tokens. Every token has a position. When you attend from one token to the other, instead of attending directly to their positions, you attend to their relative distances. You only use the relative distance. So it doesn't matter if I'm on the top right of the image or at the bottom left of the image, as long as we have exactly the same relative arrangement, okay? So indeed, you train these energy functions, and the interesting thing is that there has been a very recent progress on how to train those energy functions more effectively. Essentially, you use them demonstrated configuration as the positive example and generated configurations from the model as a negative example. And what are these generated configurations from the model? Well, you start from random, then you follow the gradient, and then you add some noise, and these are negative examples at training time. At test time, now the energy function has been trained, so you just follow its gradient and you go to the right place. Okay. So I'll show you how this work essentially. So here now the interesting thing is that you have the initial observation, and here we're going to see how, taking the gradient of that energy at every time step will put all the objects in the right places. Do you see? And do you remember how we said that despite the fact that we train on a single spatial concept at training time, at test time we can have a very long utterance with multiple concepts, and which gradient do we follow, since there are many energies, each energy representing a special concept in the scene? Does anybody remember? For example, let me give you a concrete example. By reading that utterance, it says, first of all, place the blue plate left of the lattice, okay? So there is a semantic parser here that takes that language and says, oh, I think what's happening is I need to instantiate an energy function that corresponds to the left concept. You remember that we trained a different energy function for every concept between the blue plate and the lattice. And then you ask your grounding model, where is the blue plate? In the grounding model says, here's the blue plate and here's the lattice. So you know exactly where the objects are. So you know their size and locations, and you feed them into your energy function. So now you could take gradient descent of that energy to actually relocate those two items so that they satisfy the concept. Do you understand that? But the problem is that this is not only one concept you need to satisfy, you may satisfy more. So what do we do in this case? Yes.
You sum up their energy functions.
You sum up their energy functions. And I'm a lattice, let's say, and I participate in 3 energy functions out of the 5. So my object location will be affected by gradient descent on those 3 energies. Is that clear? So different items may participate in 1 or more concepts. Okay. So here is the energy library that you train about the different concepts, and some are binary and some are multi-ary. For example, lines and circles and squares and so on require a lot of examples. And here are some benchmarks. So one is that you need to move one object to satisfy a bunch of constraints, and the other is that you need to move multiple objects to satisfy a bunch of constraints, as you see here, okay? And then you also have here some more simple ones. So you have only one special constraint and you need to build a line or a shape and so on. So these are the benchmarks we're going to evaluate multiple models. So here is the result. So the language planner, what we saw earlier, this inner monologue, even with Oracle object detection and Oracle success feedback signal, because they do use humans to say, yes, you achieve the goal or not, etc. Even with Oracle, it's still not able to achieve the task, okay? So Clipboard also fails a lot simply because abstraction, much like in that great paper we had, so guys, learning to drive with modulation and abstraction, because here first you run your object detection and you operate on top of those object detectors and their sizes and locations. The object detector works both in simulation and in the real world, right? While Clipboard doesn't go through an explicit object detection step, okay? So you change the background and like, oh, now I cannot find the blue cube anymore because that 1D language to visual feature in their product is extremely brittle, all right? While those language detectors have been trained on insane amount of data and fine-tuned, etc., so they are a little bit more robust. Still, they are not as robust as we would like them to be, just to be clear that this is an open problem, okay? And yes, so I discussed already about the problems of planning in language space, that oftentimes they are not a reasonable intermediate locations, that to put objects in a specific configuration, you need to traverse sub-goals that may not be describable in language, okay? And yeah, so without goal generation, if you do the same thing, you have a huge drop in performance, which shows how important it is first to imagine the goal and then to do essentially pick and place policies. The pick and place policy, just to be clear, is precisely transporter networks, but biased around a particular patch. So you don't ask the transporter to say, okay, pick anything here. You just ask it, okay, I found that this is the object I want to pick. Suggest to me a pick location without this sub crop of the image, okay? So here are now some execution results. So this VLM ground is exactly this language grounding that I told you. First, you need to find the different objects. Then you need to imagine their configurations. And then there is the pick and place policies that we set from transporters that go and put the objects in their corresponding locations, okay? And I mean, here again is the same thing. You give the instruction, and first you detect the objects, then you predict using gradient descent their goal locations, and then there's a policy that knows the goal and goes and step-by-step carries out the instruction, okay? And the same thing that you train in simulation, you can just deploy directly in the real world. Do you have any questions? Again, it's the same steps. First, you need to detect the objects, then you need to predict their goal configurations, and then you need to pick a place to corresponding locations. All right, but let's go back to what we said, okay? So that was the top-down approach to robotics. So it's as if we assume the low-level skills are given, all right? And then we build high-level planning algorithms. So the planner, in our case, in the third case, was like an energy minimization planner. And the energy was, let's say, composed out of the different spatial concepts guided by language. But we still assume that the low-level skills were there. I mean, we trained them with the clip, but, we didn't do anything more. We just copy-paste previous work, right? The transporter networks. Now, imagine how many horrible things can happen if you move away from those pick-and-place tasks, but you want to pick more complicated objects, or you want to pick a glass, whereas there is a particular place you want to pick it, or you want to, squeeze this sanitizer that you really need to squeeze in a very specific location, a very specific way, etc. Those low-level skills are just not there. So basically, all this approach.
Now, everything doesn't go exactly the way it's supposed to.
So the point here is the following. It's not that the robot doesn't know the task and we need a language planner to tell us the sub-goal. It is super clear what the task is. It's just to put the box in that thing, etc. So more language is not going to help the robot. So here is precisely the problem, that this takes us back to what we said in our introduction, that we think that the difficult part is the language understanding, while the difficult thing is not language understanding. The difficult thing is those mid-level, visual motor policies and skills and adaptation of those across environments that we are so good at, and our robots are really, really terrible, okay? And this is precisely, what we saw in our very, very first lecture. And this is a slide taken from Daniel Warpert, that the neuroscientist that we saw in the very first lecture, that said that brain was developed to control movement. And what Daniel is saying here is that playing chess, yes, computers are better, but picking up the piece, even a toddler can do it way better than the computer right now. Okay, so here we have put all our resources on building high-level planners, and this. I mean, I really don't like this last line of works on language, because they build plans that, as Manuela Veloso said, nobody can execute. You plan and plan for no reason, because these are not executable plans. So why don't you just focus on, what really, is hard in robots, and it's hard to open a door, because you need to control so many muscles in a very high frequency, etc. And every door is different, all right? And you need to figure out, and you need to just really, really be able to adapt across environments, and they have different ways of operating, and you need to find that door and handle, and you need to be in the correct distance as opposed to too close or too far, etc. And you bump on the door and you fall yourself backwards, and all crazy things can happen. And yeah, it's a huge search space. And even if you find the solution, so here's the thing: I give you the solution in one environment, you need to generalize the solution to another environment. So the common belief is that, low-level skills are easy. The engineers are going to take care of them. The hard thing is to do the high-level planning and to understand language and really plan in that language space. Well, the truth is that evolution has spent so much more time on developing the low-level skills for us not to be eaten by the tigers and to be able to run fast and from the rain, etc. And language has showed up very, very lately in human history. Okay, so my point is that whatever you see out there in the papers does not mean that is the real problem to address, because papers show success stories. You cannot publish unless you succeed. And it's much easier to succeed on language than to really succeed on building visual motor skills that actually generalize in the world. Okay. And so basically, there was this Foundations for Robotics workshops in Europe last week, and there Deepak gave a talk, and he said, so, have you read this paper from Stanford about foundational models? So, the most foundational model is GPT. Look, you train it on tons of data and you can use it ready for all the downstream tasks. And that's why it's so foundational. And then what Deepak makes a point here is that the high-level planning and language model is not really a foundation for robots. This is foundation for language, not even sure for language understanding, because understanding requires grounding, and grounding requires vision and action. So it's unclear here what to use language for. You just talk symbols out without grounding them everywhere or anywhere, right? But the foundation for robots is much in a different place in really understanding vision, right? Be able to figure out what are those key points of the table so that you can use the table in another environment and still put the vase in the middle and so on and so forth. As well as low-level skills, going up the stairs. Stairs may have different heights, etc. And we actually discussed about great works in this course that actually do that. They are able to achieve. Okay, so there is progress going on in all those three levels of the pyramid. But some parts of the pyramid are wider and some parts are thinner. Okay, so basically, if you cannot see and move, me adding you some language is not going to help you see and move any better. Do you see what I mean? So this doesn't mean that it is not useful. In fact, if you, again, going back to our introduction lecture, if you read the paper, 6 Lessons from Babies, one of the 6 lessons is language. Of course, we guide our children with language, and by language, they also attach concepts, and they are able to supervise the visual features, and clip that is trained from language has built very, very good visual representations for our ventral stream, not the dorsal. We showed papers that showed that clip retraining is not the best for actually using those features in the backbone of the policy. We discussed that self-supervised learning could generate better features, if you remember, for the policy backbone, right? I mean, we saw these papers. I don't know if you remember them. So now, basically, the big question is, how do we build those world models and skills for robots that are general purpose, and I'll be able to use them across contexts and environments? And the truth is that this is an open challenge in robotics. It's an open research problem. Okay, what is the right representations? How can we get this to generalize? How can we learn with very, very, very intelligent exploration and adapt our skills very, very fast? Okay, so this is an open research problem. Watching and imitating other people and really, really putting a lot of emphasis on vision, I think, is important, because by watching, you can get sub-goals. What are the sub-goals of those behaviors? If you get sub-goals, then the rewards are not far in time. If the rewards are not far in time, then reinforcement learning kind of work. I mean, probably we need to change a little bit the way we sample actions, etc. Not adding noise, which would be crazy, but the sub-goal is nearby. I mean, when you make a cake, you definitely don't want to have a reward. Oh, did my mom like the cake that I made? Who cares? This is so far away. You need to have very dense visual sub-goals about how you pick every ingredient and so on, how things are supposed to look, how you open them, flour, etc., etc. Does this make sense? And a lot of those sub-goals can be given by watching other people if you have a good, let's say, vision system, which is, let's say, an open research problem. So we don't have it, but we're, I think it's worth working towards it. And I hope you enjoyed the course. And this is our last slide. And yes, please let me know if you have any questions. We have 10 minutes, 8 minutes for questions, and then we also have office hours. Yes.
So I guess just on this, or the last couple slides, would it be accurate to say that the kind of optimizing for rewards in the past used to be like the approach for trying to solve the entire problem, but moving forward, it seems to be more like, is there still a role for optimizing for rewards to solve the entire task?
No, let's see. No, I don't think so. I think it has always been. In fact, this RL thing, learning with rewards, is a very recent field where people have attracted a lot of attention. We will always be using imitation learning, let's say. Okay. Yeah, and basically the plans are there. So if I tell you I want to make a cake, I mean, I don't need the language model to tell me the steps. I have written the recipe in my book. I'm just going to open the book and check it. Does this make sense? So the sub goals are there. I have saved them. Now I just need to execute one by one. Does this make sense?
Yeah, so the role of the RL is really more in how to execute each individual step.
I would say the role of reinforcement learning is, so it depends, by the way, what you mean by reinforcement learning. I mean, in our course, we had some chunk about model free RL and how we have a reward or a sub goal that gives us reward by matching the state to that goal. And we were trying to find actions, so that is fine. And in fact, for many behaviors, right, just we showed how, for example, Deepak Pathak was able to learn to train a cockroach robot to walk and go up the stairs only in simulation trained with reward, and the reward was not distance, either you go up the stairs or not. Okay, so in that case, this is extremely helpful where you're able to pick up the object and so on. Now, where you need to pick up the object, you don't need to train it with RL. First of all, I'm not supposed to give you the reward. I mean, the last thing I want is to start, engineering rewards of how you need to place the object. Just look at how the other person pick up the object and just do a similar thing. Okay. Now, for you to adapt to the different cups, some are soft, some are hard. Now, if you go and squeeze the hell out of the Coca-Cola can, then this is okay. Sure, you need to really practice. So there is a place for practice on your own in your simulator, and there is a place for sub-goal prediction. And this sub-goal prediction can come either from passive data or from active data. Okay. Other questions? Okay, great. So we haven't still decided about what paper will be on your quiz 3, but we will do our best to be super fun. Okay. So, like fun, so that this is a fun quiz. And best of luck for your studying. Okay. And best of luck for Monday, 8:30 in the morning. I heard it is the, yeah. Okay.